All right, welcome back. So let's take a couple more examples. We're still looking for the area between two curves. And in this case right here, we have the parabola x equals 5 minus y squared and x equals y minus 1. Now, the first thing I notice is that we are now in terms of y, which means that we are going to use a horizontal rectangle. So let's go ahead and graph these. The first one is just y equals 5 minus y squared. This is a sideways parabola starting at 5, and we open towards the y-axis this time. The other one is a line. Now, graphing lines is always kind of tricky for me in terms of x, so I always like to find the intercepts. So if I let x be 0, y is 1. And if I let x be, y be 0, excuse me, x is going to be negative 1. So there we go, right there, like negative 1. And we can kind of draw it. Whoop, kind of go a little bit further there. And we can again see the region that we're actually trying to shade in here. But now, again, because I'm in terms of y, I'm going to draw my rectangle horizontally this time. So let's take a look at what that would look like. It would look something like this in the graph. There it is. And I might draw another one right here too. There we go. And there's our rectangle right there. There's our rectangle of math. Always graph it. It is very helpful for us. And then I'm going to kind of blow it up down here. Now be very careful again. The skinny part here, that's our dy this time because it's vertical. It's my vertical axis, like x is vertical always. Down here to get my length again, I have to look at the change in my x values. But to get this, our rule from up top says if we're in terms of y up here, we are going to go right minus left. And that's what we're going to do down here. We're going to take the right function, which is our parabola, this 5 minus y squared, minus the function on the left, which is our line, y minus 1. Don't forget parentheses, very important. Combining your like terms, we get 5 minus the negative 1. We get 6 minus y squared minus y. So the area is just going to be the following, the integral. We're going to take that length that we just found, 6 minus y squared minus y. Remember, we're just trying to find the area of this rectangle. We take the length that we found, multiply by the width. So multiply that by dy right there. We still need our bounds, so let's go ahead and get those. To get the bounds, we just set the two equations equal to each other. And again, notice we're in terms of y. That's a really big thing to do. We're in terms of y. So bring this over, whoops, equals. We're going to get y squared plus y. Bring the 5 over, minus 6 equals 0. Factor this. We're not going to give you two hard ones yet. X, let's see here, plus 3. Oops, sorry, y plus 3. Y minus 2 equals 0. And we get negative 3 and 2. So there we go, negative 3 to 2. That would give us our area. And this one's not that hard to solve, integrating. We get 6y minus y cubed over 3 minus y squared over 2, and we evaluate that from negative 3 to 2. Doing the FTC, you know me. Don't be fancy, just get an answer. Plug in the 2, we get 12 minus 8 thirds minus 4 halves, whatever that is. Plug in the negative 3 now, we're going to get negative 18. Oh, be careful. Negative 3 cubed is negative 27, but we got that negative out there as well, so that becomes a plus, plus 27 over 3, and this becomes minus, and we're squaring negative 3, so that becomes 9 halves. And there's your answer. Just leave it alone. That's it. All right, so go ahead and pause the video here if you want to try one. Take a look at number 3 here real fast. I'm going to go ahead and work it. So the first one is a line. So I'm just going to draw this line. We want to find the area bounded between the line. So I'm going to graph that line. Y equals 2x plus 5. So there's 5, and there's y equals 2x plus 5. Nothing accurate. Here we have the parabola, x squared plus 2x plus 1. I'm going to go ahead and factor that. That's x plus 1 squared. So that's basically, let's see here. I shifted over to the left one, and it's going to look kind of like this. There we go. We're not looking for accuracy, but I do want to say this. You want to be able to see the region in between here. Now, I know this is going to have a shift of left 1 because of our algebra, x squared, x plus 1 squared. That's my horizontal shift, that plus 1, so we go backwards. So here we go. Notice we are in terms of x. So what does that tell us about our rectangle? It's going to be vertical. Keeps it really simple. Vertical is in terms of x, horizontal in terms of y. So I can do this one. I draw my vertical rectangle. There it is in my graph. And if I blow it up on the outside here, notice the skinny part now is horizontal. That's my change in x. We have to find just the length. So to get the length, this is our change in y. And our rule says it's going to be the top function minus the bottom function. Well, what function's on top? That's just our line, 2x plus 5, minus the bottom, which is that parabola. There it is, there's the bottom, x squared plus 2x plus 1. Clean it up a little bit, not that bad to do. We would get 2x minus 2x, so the x's just cancel, 5 minus 1, so we get 4 minus x squared. And there's our function. There's our length. So to get the area of our rectangle, we're going to take the length that we just found and multiply it by that width of dx. It's just the length of a rectangle. Length times width. And that's literally what we're doing here, right? We just talked about this. This is literally length times width, and that's it. And remember, this is the only for one tiny, skinny little rectangle. We have infinitely many of them. So, whoop, there we go. My width disappeared. So what we need to do is we need to integrate it to add all of them, because not only do we have this rectangle here, but we have infinitely many little rectangles that we have to find the areas of. And the integrand just adds up an infinite number of whatever it is we want to find. So let's take a look at this. So what does the integral tell us to do? It adds things. It adds things. Not just things, but an infinite number of things. That's what it does for us. All right, so now we just have to get our bounds. To get the bounds, set the two equations equal to each other. 2x plus 5 equal to x squared plus 2x plus 1. And the 2x's cancel, which is nice. And we would get x squared minus 4 equals 0, or x equals plus or minus 2. And that's our domain, from negative 2 to 2. We can integrate this now. We get 4x minus x cubed over 3 from negative 2 to 2. Use the FTC, f of 2 minus f of negative 2. Let's see what we get here. That's going to become 8 minus 8 thirds. Plug in negative 2, negative 8. Be careful, a negative 2 cubed is negative 8, but we've got another negative out here. And that becomes a plus 8 thirds. Don't simplify them. Please don't say, oh, look, they cancel. They don't. Leave it alone. All right, try one in terms of y. So notice here, we have one, we're in terms of y now. We have x minus 9 minus y squared, and x equals 5. We are in terms of y, because it's solved for x, in terms of y. Therefore, this time we're going to deal with a horizontal rectangle. I'm going to graph it. 9 minus y squared, that's just a parabola. There's 9, and it opens on the x, and it opens down towards the y. There we go. X equals 5 is just a vertical line. And we want to shade the region in between them. There we go. Now notice we are in terms of y. So I'm going to make my rectangle horizontal. We can make it vertical. It just makes it more hard to do. We'll take a look at an example like that. So let's make our rectangle horizontal. Horizontal means it's going to be flat like this. Now remember, this is just a representation. This is only one rectangle. Remember, there are infinitely many of them, rectangle, rectangle, and we're just going to, kind of like an old paint program, we press up here and just going to fill in the area for us, right, like that is what it's going to do. It's just going to fill in the area. So we're going to make it just generic right here. So this is the rectangle we're going to use. Blow up your rectangle. Be careful, it's horizontal. So my skinny part is vertical, so that's going to be my dy. The skinny is always dy, because remember, this is so skinny, it's really 0. So let's talk about that dy, what that dy really means again. Dy is really the limit as delta x goes to 0. This is, or I guess in this case, it should be delta y goes to 0. There we go. It's the limit as delta y goes to 0. So effectively, it's just 0. So this is really saying that we have a rectangle of 0 width right there. And that's really kind of interesting because we're going to add up a bunch of zeros here and get a number. Crazy. So we still need to get the length, but this time it's my horizontal length, so it's going to be delta x, and our rule says to take the right minus the left. So if I go over here, which function's on the right side? It's our parabola, 9 minus y squared. Which function's on the left? It's our line x equals 5. And I can clean it up. This becomes just 9 minus 5, which is 4 minus y squared. And we just multiply our length times our width to get our area. So we're going to take this 4 minus y squared multiplied by dy. Now we have to get the bounds. Be very careful. You're going to want to say from 5 to 9, but be careful. We have to be in terms of y as well. So to get the bounds, we're going to set our functions equal to each other. 9 minus y squared equals 5. We basically get 4 minus y squared equals 0, so y is again plus or minus 2. I just plug it in. Integrating, we get 4y minus y cubed over 3 from negative 2 to 2. And let's see here. And look at that, almost the same. It should be the same as the last problem. That's kind of boring. All right, so if we plug in the 2, we get 8 minus 8 thirds. Minus plug in the negative 2, negative 8 plus 8 thirds. You can verify that. There's our f of 2 minus f of negative 2 right there if you want to take a look. All right, going to the next video, we'll take a look at a few more examples. I'll see you then.